Hello and welcome to Questions of Light. My name is Craig, and in this show we're going to take a closer look at what light is, how we can use light in our technology, what we can learn by studying different types of light, and also do some cool tricks involving light. Now when we study light, the best place to start is something called the electromagnetic spectrum. So let's take a closer look. The electromagnetic spectrum is a scale of 7 different types of light, some of which you may have heard of before, and most of it is invisible to us. It contains radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, and gamma rays. Now at a basic level, light moves up and down as a wave. And at one end of this scale, the waves can be meters in length. And at the other end of the scale, they can be extremely small, even smaller than the width of an atom. This is called its wavelength. So let's start by looking at the light that we can see, which sits in the middle of our electromagnetic spectrum, our visible light. In the 17th century, Sir Isaac Newton shone some sunlight through a glass triangle called a prism, and split that white light into the colours of visible light. Here I am repeating that same experiment using an LED lamp, with the white light moving through the prism and splitting into red, orange, yellow, green, blue, indigo, and violet. The reason this can happen is because light can bend or refract through materials. When I shine a laser through the prism, you can see the light bend slightly and change direction when entering, and then bend even slightly more when exiting the prism. Since each colour has a different wavelength, it means they bend slightly differently through the prism, resulting in a nice spread of colour when the light exits. Now you may have seen these colours in the sky as a rainbow, and a rainbow appears because of the exact same reason. When it rains, light from the sun passes through each drop and splits into the visible light colours, forming the beautiful band through the sky. Because a rainbow is not physical, then it means that the rainbow you see is actually different to the rainbow seen by someone next to you. But with all of these colours of light available, why then is the sky blue? When sunlight enters the Earth's atmosphere, the blue light gets scattered by gases such as nitrogen and oxygen, as their atoms are of a similar size, resulting in the blue light remaining in the sky. This is known as Rayleigh scattering. As the sun sets though, its light has to travel even further through the atmosphere, resulting in even more blue light being scattered, and only the yellow and red light being let through. This is the reason why we get red sunrises and sunsets. Radio waves are a great way of transmitting information through the air, as they can travel through buildings and are not harmful to the human body. This makes them great for communications, particularly for TV, mobile phones, and the standard radio that you might find in your car. Information such as voice, music, or video is coded into a radio wave, which is then sent out from an antenna, before being received by a separate antenna, which is then decoded and broadcast through your TV, phone, and radio. Since radio waves aren't affected by the atmosphere, that makes them ideal for global communications, transmitting information between satellites positioned around our planet. They can also be used for GPS and radar systems, which are key to the navigation of cars, ships, and planes. Radio waves are strictly regulated by governments though, as certain types are reserved for certain tasks. For example, if someone were to accidentally use a specific radio bandwidth that interferes with radar, then it could be very dangerous for directing planes around the country. Microwaves are unique in that they can put their energy just below the surface of a material, and this makes them ideal for heating up food, which has led to the invention of the microwave oven. A microwave oven works by sending microwaves in all directions, which are then reflected within the metal interior of the oven before being absorbed by the food. The microwaves cause the water molecules inside the food to vibrate, producing heat that cooks the food. In 1964, two scientists named Arno Penzias and Robert Wilson were experimenting with a 6-meter long antennae, which was designed to detect radio waves. To do this, they had to remove all background lights. But in doing so, they discovered an even spread of microwaves across the sky, which was present during daytime and nighttime. What they had accidentally discovered was the cosmic microwave background radiation, which was the leftovers from the Big Bang at the very beginning of our universe. Over the following years, measuring this data allows scientists to produce this colourful picture, which shows changes in temperature. It also gave an average temperature of the universe of -270 degrees Celsius. Over time, further investigations have made this picture more accurate, going from this in 1990 to this in 2013. You can detect this background radiation using your radio, simply by tuning it to in-between stations. NASA famously said that if you ever get bored of listening to the same songs, you could always tune it to the birth of the universe. Two centuries after Isaac Newton first used a prism to split sunlight into the colours of visible light, another scientist called William Herschel repeated his experiment. Except this time, he placed a thermometer in the red light. He also placed a second thermometer just beyond the red light and had a third thermometer to measure the room temperature. What he discovered was that the red light was hotter than the room temperature, which wasn't unexpected. But when he checked the second thermometer, he found that it was even hotter still, which meant that there was an invisible source of light just beyond the red light. This light became known as infrared. A thermal imaging camera can detect infrared light and produce an image of the heat in the area around them. This can be useful for the emergency services, particularly the fire service, who can use thermal imaging cameras to enter a smoke-filled room and rescue anyone inside. Infrared light can be used to help us learn more about the universe around us. Take this image of the nearest galaxy to our own, the Andromeda Galaxy. This is the light we can see with our eyes, and you'll notice there's lots of gas swirling around the galaxy. However, when we take an infrared image of Andromeda, we find we can see a lot more detail hidden behind this gas. And this gives us a better idea of what is happening inside the galaxy. Infrared light can also be used for sensors and remote controls, as well as to detect your heartbeat and oxygen level using a smartwatch. It can also be used to predict weather patterns through satellite imaging. On the other side of visible light, we have ultraviolet light, or UV light, which, as its name suggests, is a type of invisible light just beyond violet light. And it is at these wavelengths that light starts to get more dangerous as it becomes more intense. One of the biggest producers of UV light is the sun, and if all the UV light from the sun reached the surface of the Earth, then life as we know it would not be able to exist. Fortunately though, the Earth's atmosphere is able to block 77% of UV light from the sun, forming a protective bubble around our planet. A good portion of UV light still reaches the Earth's surface, however, which can be dangerous for human beings. Particularly on sunny days, long exposure to UV light can result in sunburn on your skin and also damage your eyes. Which is why it's important to stay in the shade, wear a hat, and put on sunscreen. Here we have the same footage of someone putting on some sunscreen, the left hand side showing us the visible light and the right hand side capturing the ultraviolet light. The reason it looks darker is because the sunscreen is blocking the UV light and protecting their skin. UV light isn't all bad though, but only in small quantities. 15 minutes of sunlight every day, even when it's cloudy, can help boost your vitamin D levels. And doctors regularly prescribe time on sunbeds to help treat some skin conditions. UV light can also be used to sterilise or clean medical equipment, as well as prevent forgery on banknotes and passports by adding details that can only be revealed using a UV light. Some animals, including birds, reptiles and insects, can see near ultraviolet light, which cause fruit, plants and other animals to stand out more strongly from the background. For example, scorpions glow green when viewed under ultraviolet light, which can also reveal beautiful patterns on plants and birds. When I was 8 years old, I fractured my left wrist, which, if you've ever broken a bone before, isn't the most pleasant of experiences. However, one of the upsides of doing so was that I got to have an X-ray to see where the break was. X-rays are ideal for this situation because they can pass through your skin and flesh, but not your bone. Which is why, when you place a sensitive plate behind your hand and shine X-rays through it, you get black portions where X-rays have passed straight through, and white portions where they have been blocked by the bone. X-rays are very dangerous in high doses though, which is why the doctors who use them have to stand behind a protective shield or even leave the room completely to limit their exposure. X-rays can also be used to take photographs at the tiny atomic level. One of the most famous X-ray images is Photo 51, which was taken in 1952 by Raymond Gosling, who's been supervised by Rosalind Franklin. It showed the pattern of DNA, which is the biological instructions for every living thing. When Maurice Wilkins became Gosling's new supervisor, he passed on the photo to James Watson and Francis Crick, who were able to use it to help determine the double helix shape for DNA. The three men were awarded the Nobel Prize for Physiology or Medicine in 1962, but controversially, neither Rosalind Franklin or Raymond Gosling were acknowledged for their part in its discovery. The final type of light in our electromagnetic spectrum is gamma rays, which are by far the most dangerous as they can move through almost any material. Sometimes known as gamma radiation, it can prove fatal to humans in large doses, as it can break down our cells and cause our bodies to shut down. One of the main sources of gamma rays is in nuclear reactions, and at a nuclear power station, every radioactive material is covered by either thick lead containers or huge amounts of water to prevent gamma radiation from escaping and affecting the health of the staff and the local environment. The nearest and largest nuclear reaction to us is at the centre of our Sun, and it throws out huge solar flares at the Earth every single day, including some gamma rays. Luckily though, we have a unique shield that protects us. The Earth has a magnetic field that runs from the North Pole to the South Pole, which is caused by molten magma moving in the Earth's core. This magnetic field deflects the harmful particles of a solar flare over and away from the Earth, keeping us safe. The Earth's atmosphere also prevents gamma rays from reaching the surface. Sometimes these solar flare particles are funneled by the magnetic field into the North Pole, causing a unique phenomenon known as the aurora borealis. You may recognise this by another name, the northern lights, which are caused by the sun's particles reacting with the gases in the Earth's atmosphere, producing flashes of green and blue through the sky. On a clear night, these can sometimes be seen in the north of Scotland. Some animals or plants are able to produce their own glowing light, which can be used for communication, camouflage, or attracting prey. This is a process called bioluminescence. It is produced by a chemical reaction inside their bodies, and is used by animals such as fireflies, glowworms, algae, and even some fish. One of the most famous examples is the anglerfish, which uses a glowing modified fin to attract prey in the deepest parts of the ocean. These reactions can be reproduced using a chemical called luminol, and when mixed in with some water, bleach, and another chemical, it produces a beautiful blue glow. It is a type of chemiluminescence, which is unique in that it produces light but not heat. This is the same process that happens in glow sticks. When you crack a glow stick, two chemicals mix together to produce the glowing light, and depending on its makeup, they can shine for minutes up to days. The hotter the temperature is though, the faster the reaction will happen. So if you want your glow stick to last longer, you can always pop it in a fridge or some ice. Here I have a plasma ball, which contains an electrode in its centre and is filled with a mixture of noble gases such as neon and argon. When it's switched on, electricity passes through these gas particles, producing beams of plasma which reach out to the glass dome. If I place my hand on top of the globe, then I can direct these plasma beams towards me, as electricity always wants to find the best path towards the ground. You will probably find that your classroom or office is lit using fluorescent light bulbs, which work in a similar way. Inside, there's a gas that reacts with electricity to produce light. And this is much more efficient than using your standard filament bulbs, so much so that the fluorescent bulb can be lit using the plasma bulb. Now Now, the reason our eyes can see light is because light can reflect or refract, which means it can bounce or bend through materials. Now, how much light can bend through a material is called its refractive index. And most materials have a different refractive index from another. For example, air has a different refractive index from water, which has a different refractive index from glass. However, if you were to put two materials together which have the same refractive index, then the light passes through without bending. And that means our eyes don't pick it up. And that actually makes it appear to look invisible. For example, here I have a Perspex glass test tube, and I have a big jug of oil. Now, Perspex and oil have the same refractive index, which means if I place this test tube into the oil, it will look as if it's disappeared. So let's have a look. There we go. So as you can see, the test tube has completely disappeared. Now, I know what you're thinking. You can still see something inside the oil. That is actually the air inside the test tube. And because air has a different refractive index to the oil, it means our eyes can still pick it up, which means we can still see it. But watch what happens when I fill up the test tube with oil. So now it looks as if it's completely disappeared. So let's show you that again. I'll empty the oil. So if I put the glass test tube into the oil, you can still see the air inside. But if I fill it up with the oil, slowly but surely, it looks as if it is turning invisible because it has the same refractive index. There we go. Ah, no. I've dropped it. Oh dear, that's not very good. Hang on. Let me try and get it out. Thing, because it's invisible, it's hard to see. I think I feel it here. Okay. There we go. There's our test tube. Pour out the oil. Do you know what? I actually felt something else that was inside there. Let me have another look. Actually, here is another test tube in our oil, which is left over from practicing earlier. And actually, I think I felt something else. Another one in here. There we go. Number 3 test tubes. And do you know what? I think there's one more to find as well. There we go. Number 4. This experiment worked so well that the entire time I've been performing it, I've actually had a conical flask inside our jar of oil.